Welcome to the first video. We're going to cover in this video section 2.5 in your book, and this deals with Cartesian coordinate systems. The first point is that we'll be using right-handed systems. What that means is that if you point your thumb in the direction of the point your thumb in the direction of the z-axis of the system, then your fingers will curl from the x to the y. So, referring to the figure, you have your thumb in the direction of the z-axis and your fingers pointing in the x, and then they would curl in the direction of the y. So that's the definition of a right-handed coordinate system. And that way, given the x and y vectors, you know which direction the z-axis points. It's always going to be perpendicular to the other two, but it could be one direction or the other. So defining it as a right-handed coordinate system constrains the direction that the z is going to point. So x, y, z. And again, now we're looking at 3D systems. So just like in the 2D systems, we have rectangular components. Starting off with a vector A. I'm going to go turn off the lights. Hopefully it'll help. That looks better. Vector A. And this can be decomposed into components that are perpendicular, and this is referring to the figure on your right. So we have A prime and AZ. A prime is the component of A that's in the XY plane, and it's shown in the figure with the dotted line. And if we add to that the vector AZ, which is the component of A in the z direction, then we'll get A. So this is one decomposition. We have a component in the XY plane, and then we have a component in the z direction. So A is equal to A prime plus AZ. And we can also decompose it further into AX, AY, and AZ. And all of these are vectors. So we have AX, which is a component in the x direction, AY is a component in the y direction, and AZ that we saw before. And if we wanted to represent this, so this is the rectangular decomposition. And then we can use Cartesian coordinates, like we did in 2D, and say that A is equal to the magnitude of AX times the I direction vector plus AY times the J direction vector plus AZ times K. I'm just going to check if that's legible. All right, it looks legible. So there is rectangular decomposition. We have the vector, and we're getting components that are perpendicular. This is perpendicular to that, and these three are also all perpendicular. And then here it is written in Cartesian coordinates. We've got the magnitude AX times the I direction, magnitude AY times the J direction, and magnitude AZ times the K direction. And talking about magnitudes, if we wanted to find the magnitude of A, the vector A, that's given by the square root of the sum of the squares, just like in 2D. So we have the x component squared, magnitude of the y component squared, magnitude of the z component squared, and the square root of all those. So it's basically the same equation for 3D as it was in 2D. Just now we're adding this Z component. So just a minute. Now we have covered the decomposition of a vector into rectangular components in 3D. We've looked at the Cartesian representation and the magnitude. So now we'll look at the direction of a vector in 3D. So we have a 3D vector. Oops. Still referring to that figure, the first one. We have a vector in 3D, and again, I'll write it's write in Cartesian form. The magnitude in the y times the j direction plus magnitude of the z component times the k direction. And if we want to get a direction vector, so a direction vector is just the same thing as this vector except it has a magnitude of 1. So that way it doesn't carry any magnitude with it, so it's normalized, I guess. Anyway, it's a unit vector in the direction of this, and so that's defined as follows. So we'll write u sub a, and again a hat to indicate that it has a magnitude of 1. So u sub a, and here's the equation for it, is equal to the vector a divided by the magnitude of the vector a. So this is scalar multiplication. We have a vector a, and then we're multiplying it by 1 over its magnitude. So that'll give us a new vector that's in the same direction of a, but with a magnitude of only 1. And we can expand that as the x component over a in the I direction plus the y component of a in the j direction, or divided by a. The z component divided by the magnitude of a in the k direction. And so that is a direction vector in the a direction. And we'll use this a lot whenever we want to find a force along the line. So we'll know 2 points on the line. Say, we had the geometry of a structure. And so that gives us 2 points along a line, a cable or something. But we just want to know, we want to get a vector representation of the tension of that cable. So first we could find the direction vector of that cable and then multiply it by a magnitude of the tension. And that will give us a vector representation for that force. And hopefully that'll become clear later. Now the next topic deals with this figure on the right. And this has to do with finding the Cartesian components whenever you're given this representation of a vector in 3D. So we saw in 2D that a vector could be represented with like a magnitude, in this case 10, and then an angle 20 degrees. And so you can get the x and y components from that. The x component is 10 times cosine of 20, and the y component is 10 times sine 20. Similarly, the direction and magnitude can be given in 3D with 2 angles and a magnitude. So in the figure on the right, we have 2 angles, theta and phi, and we have the magnitude of A. And this is the same rectangular components that we looked at before, where we have a component in the xy plane, which we call A prime, and then a component in the z direction, AZ. And you see A prime at the bottom of the figure next to the gray shaded triangle, and then AZ is along the z-axis. So For this figure, I'll write equations for a prime and az, but you need to be careful because it depends on how the angles are defined. So in this case, the angle phi is defined relative to the z-axis. In some cases, it might be defined relative to the xy plane. And in that case, these equations don't work. The point is, just look at the geometry and think about the definition of cosine and sine, and that way you can get the components. So we have AZ, and again, this is just a magnitude. We already know the direction of AZ. It's in the direction of the K unit vector. So the magnitude AZ is equal to the magnitude of A times the cosine of phi. So magnitude of AZ is A times cosine of phi, and here's a triangle. So there's phi and A. And so that relates to the figure on your right. We got AZ, A, and then the angle phi. And so you can see that this side of the triangle is that times cosine of phi. And if you don't remember that, then study cosine and sine and make sure that you're familiar with these and you can do those quickly. And then the definition for, well, I wouldn't say the definition, but because it differs depending on how the angle phi is defined. So in this figure, the magnitude of A prime is just A times the sine of phi. And I should have erased that figure. So we have A prime, the magnitude A prime, magnitude AZ, magnitude A, and there's phi. So A prime is A times the sine of phi. And if we want to go ahead and get the Cartesian or the other rectangular components, so AX and AY, then we're just going to use A prime. Because if you look at that figure on the right there, then A prime is composed of AX and AY. So, in other words, the vector A prime is equal to the vector AX plus the vector AY. And here are the equations for getting AX and AY, the magnitudes. So AX is equal to the magnitude A prime. And then again, we have to look and see how the angle theta is defined. In this case, theta is relative to the x-axis. In another problem or situation, it might be defined relative to the y-axis. So these sine and cosine would switch, would change order. We'd have cosine instead of sine, sine instead of cosine. But in this case, with theta defined relative to the x, then the magnitude AX is equal to the magnitude A prime times cosine of theta. And that's also equal to substituting from this equation, A sine phi cosine theta. And then AY is just A prime times sine of theta. And again, these are magnitudes. This is not a vector. This is the magnitude of the component in the y direction. So again, here's the vector sum. The vector A is equal to the magnitude AX times the I vector plus the magnitude AY times the J vector plus the magnitude AZ times the K vector. So we have the scalar multiplication of these direction vectors, I, J, and K, and that gives us, that vector addition will give us the vector A. So you can see in the figure there on the right, we've got AX plus vector AY plus vector AZ is equal to A. Now we'll look at a scenario where you're given a direction and a magnitude. So we're given this direction vector, UA, and we're given a magnitude, A. And we want to find the x, y, and z components of A. So find AX, AY, and AZ. And these are all magnitudes. So that's where A is equal to, again, AX I hat plus AY J hat plus AZ K hat. Okay, so we're given the direction and the magnitude, and we want to find the components. We'll start by referring to the definition of UA. So UA is equal to the vector A over A. And we can expand that into AX over A times I hat, AY over A times J hat, AZ over A times K hat. And all these terms, and you probably get tired of me saying this, but we just need to be really straight about it. All these terms in parentheses are scalars. So we've got scalar multiplication by these direction vectors, I, J, and K. We're multiplying I by this number, AX over A. Okay, so we want to find AX, AY, and AZ. Okay, so we could go about it a couple different ways. I'd say that the easiest way is just to multiply both sides by this magnitude A. So the vector A is equal to the magnitude A times the direction vector UA. And so that will give us A times UAX, the x component of UA in the I direction, plus A times UAY in the J direction, plus A times UAZ in the K direction. So when we have this vector UA, it's going to have components in the I, J, and K directions. And those are UAX, UAY, and UAZ. And so we'll just multiply the magnitude of A times those different components. And then that will give us, so here we have two different definitions of the vector A. AX times I, and that's equal to the magnitude A times UAX. And the same thing, AY is equal to magnitude A times UAY. So we simply use this definition here to get, actually we use this definition. The vector A is the magnitude of A times the direction vector, u sub A. And we'll do an example problem. So we have here a vector, and we know its magnitude is 100 pounds, so this is a force vector. And its direction is given with two angles, one relative to the x-axis, it's 45 degrees, and one relative to the xy plane, which is 60 degrees. So we want to find the rectangular or Cartesian components. So we have, we'll start off, A is equal to A prime plus AZ. And AZ is the simplest to get, so we'll get that magnitude. The magnitude AZ is equal to the magnitude of A times, in this case, is it cosine or sine of 60? We've got sine of 60 because of how it's defined. So if you look at that light blue triangle, you see the vertical side is opposite the angle 60 degrees. So that tells you need to use sine. So AZ, the magnitude AZ is A times sine of 60. And then the magnitude A prime should follow from that, or you should be able to see it from this one. It's cosine of 60. If you look at that light blue triangle, the side that's next to the 60 degrees is A prime. So that tells you it's cosine of 60. Now that we have A prime, we can get AX and AY because the vector A prime is equal to vector AX plus vector AY. So now we'll deal with the magnitudes. Magnitude AX is equal to magnitude A prime, and then look at the angle 45 degrees, see how it's defined, what axis it's relative to. So you can't just use a straight equation all the time in these situations. You have to look at the angle and think about the trig definitions for sine and cosine, and also see which direction the components are pointing for, if it's positive or negative. So magnitude AX is A prime times cosine of 45. And then AY is A prime sine of 45. But I almost went too fast. It's in the negative y direction. So it's negative A prime sine of 45. Okay. So now we have AZ, AX, and AY. For AX and AY, you'll have to use A prime, and you found that magnitude here. And so you can either substitute in A cosine 60 times cosine 45, or you can just store this value and use it here. And again, if you want to write it down, make sure you keep at least 5 significant figures for A prime whenever you use it over here in this equation. And then another example problem. Okay. That example problem is in the next section. So we'll stop this recording here.